I have the instructions on how to read this in R. And finally, when you after reading this and making this variable a factor, then you can save the image, or you can save in R data image. You know how to do it now, right? Okay. Just say save this SA part comma and then file equal. So that's where space right. Either way, you prefer to do. So either do that or just this. Do the same image, save your global environment, your working space as a permanent image. So tag with your permanent the R data file. So if you want to use a new one, okay. For example, okay, so you can choose to save to this R image file just by itself, or you can just put it as a part of your global environment. And I have the specific instruction on the dividing this into a trend set and test set. So anyway, just use that. And particularly this one is also focused on running the variable importance as well, in addition to supervised learning. Ask you to do two classifiers using the neural network classifier and simple vector machine. Okay, so anyway, so this will be the case study number 4. And the due date is Tuesday, November 20th. Okay. You have 2 weeks to work on. Is that enough time or not? Start looking at it, okay? This is data set from this Elements of Statistical Learning books. It's on that web page. You can go and fetch this data set just by this. So anyway, I let you just read this, and actually you can use this code here to create this data set. And the split is down right there. I guess I didn't ask you to put a seed here, but you probably want to run a set C before you do this random sampling. So you might want to add this set C before that. Okay. And then here, whatever C's you decide to set up. Okay. So here 1, 2, 3, for example. So run this set C before you actually perform this stage. Okay. Or if you want, you can do this more than once, splitting this into 40-60% splits. Just do it more than once, maybe 2-3 times. Okay. Just in case of that. Okay, so that's about this. Do you have any question? See, the codes I put in here to maintain the proper proportions of these two classes is done by this, or with this 40%, 60% split. So that you try to do that. Okay, so that's about the case study number 4. Okay, we're going to talk about random forest today. This is one of 3 this ensemble learning or ensemble methods that we actually talked about 2 of these 3 this ensemble methods before. Just look at our class note. So random forest for classification. Of course, random forest is not only applicable to random to the classification. You can also do this in building up the regression forest, regression trees. It's a forest of regression trees. You can also use to do unsupervised learning. This random forest is particularly suitable for doing this unsupervised learning as well, for clustering. Okay. Which we will cover again in the future when we talk about unsupervised learning. Ensemble learning is basically a prediction model formed by combining the strengths of, say, experts, well, those called experts, okay? The strengths of a collection of simpler base models, okay? And they emphasize on this, you train individual models to become better, so sort of experts, okay? And then you combine all this, the opinions from all experts, they vote on the result. So basically that's the idea, right? Voting is for classifications, and taking average predicted response to be one useful regressions or other tasking. But here we will talk about using this ensemble learning, the random forest for unsupervised learning. Okay. Maybe I should refresh the memory. I'm not sure if you remember that when we talk about this ensemble learning. Okay. By the way, is my pronunciation correct? Is it pronounced ensemble or probably? Okay. This is French word, right? Isn't it? One is bagging. I think we talked about this before. This is bootstrap aggregation, right? We talked about this before, right? B for bootstrap, AGG for aggregate, right? Bootstrap aggregating. Okay, that's ensemble learning as well. And then we talk about boosting. Boosting is focused on training the weak learner to become better, and usually they focus more on the hard to classify observations. Okay? So make it make the result more stronger. So here, the idea of this, and then the one that we talk about here, this random forest.
Tagging, boosting.
I think we talked about this before. In a sense, random forest is generalizations of bagging, or bagging is a special case of that. Okay. In the sense that in bagging, we actually create a tree model using all predictors. Okay. Means all the input variables are involved. Okay. So all input variables are involved, and then we create a set of trees. Or in that sense, we actually build a forest as well, right? So that we bootstrap sample with replacement. Okay. So again, we use all input variables and a subset of your trained set to build up trees, and then you sort of validate on those observations not included in the bootstrap sample. Okay. And usually there's a term for that. It's called out-of-bag. It's OOBs anyway. Out-of-bag sample. Okay. Okay. Yeah. We're going to see this later. Okay, so all input variables are involved, And then you build just a set of trees, usually like maybe, I think it's default is like, I'm not sure whether it's default, probably 500 trees or less number of trees, maybe 200. Yeah. So in a sense, this is a random forest, but with no more restricted result on, say, you have to include all input variables in each tree model you build up in the forest. Okay. Where the random forest, we only use a subset of input variables. Okay. So that's the difference between this Bayesian and random forest. Okay. I should add this as a kind of slide. I didn't do it. Okay. So otherwise, these two methods are sort of similar. Okay. So Bayesian is just a special case of random forest. Okay. Of course, when we say subset, we could have this is just the subset, the entire set of input variables as one of the subsets. Usually, random forest, in a sense, we use a much less trees with much less number of input variables. That's the general idea of the random forest. Okay. So they start with simpler models which involves only a small number of variables. And then each tree is like that. And then you have forests of trees, maybe 1,000 trees. And all these trees are trained, and then they come together and vote for the final result. Okay. So this is the random forest. That's the basic idea of the random forest. Okay. So random. Basically, this ensemble learning first develops a population of base learners from the training data, and then combine them to form this composite predictor. And in case of regression, you can use average predicted result, right? That's a final the fitted value. Oh, okay, I do have this here. Okay. You have this Bayesian builds different learners by training on bootstrap samples from the data, but all the input variables are involved. Okay. And boosting combines simple base learners. Okay. These are weak learners by upweighting misclassified data points. For those hard to classify data points, we basically train this weak learner to focus more on those and try to make it better. And there are some other ensemble methods, right? But usually, these are the three that usually are mentioned in ensemble learning. Committee methods. Well, committee method means voting, right? So here this is like a general result as well. Okay. Committee methods in general, such as stacking and dictionary method, okay, which we're not cover this. And Bayesian method for non-parametric regression. Usually is formed, a large number of candidate models are formed and they average with respect to the posterior distribution. So that of this idea, like just sort of that. And random forest average a committee of randomly created tree learners. So in a sense, this is random statistical method. Think careful about this, the element of it. So actually that means that because of this randomness, okay, so we would not try to interpret result, okay, just kind of consider as deterministic. There are some researchers recently they try to modify this random forest. This particular, I remember, I think it's this also focus on somewhat semi-deterministic model rather than random forest, okay, to modify the idea of random forest. Anyway, let's look at random forest. This is the same author who proposed this method. I think naturally, right? Bayesian was proposed in 1994, and then here random forest in 2001. It's a substantial modification of Bayesian that builds large collections of these decorrelated trees. The things happen is that because all input variables are involved, and some of these variables are somewhat correlated, right, in many data sets. Okay? So somewhat the backend tends the backend model tends to build up more correlated trees. Okay, so the idea they end up to that correlated tree end up to boost up the training error and the generalization error as well. So that's the idea they come up with using this method, random forest. Try to decorrelate trees. The idea is that instead of draw, say, bootstrap samples from training set, okay, of size n. Right, there's a modification of that as well. Instead of using the complete train set, okay, some would suggest use only a fraction of this complete train set, maybe 2/3 or something. Okay, instead. Okay. Anyway, let's look at here. Draw B bootstrap samples from training set of size n. Here, this the original algorithm suggests using the complete train set. Okay, but doing the bootstrap samples means a sampling with resonance, right? Okay. And then preset minimum node sizes, which means that if node go beyond the minimum threshold, then split will no longer be performed, right? So that just end up with that terminal node. And you select n variables randomly from the P predictors. Okay. I think that's the most important features of random forest comparing to the original backend idea, is that only a subset of variables will be involved in each tree. Okay. So n variables randomly selected from P predictor. So here this is another element of randomness, right? So this is a random statistical method. And then you pick the best variable split points among the n, and then split the nodes into two dependent nodes. Right? So basically, that part is just going individual trees and form forest. And then output the ensemble of trees. So here you have this ensemble of trees out of this B bootstrap samples, and they come together and vote for the result. Because for classification, it's done by voting. So majority vote, okay, prevail. So in this case, if for say B is a random forest tree, okay, this predict class membership, then you use majority votes anyway. Okay. So and regression tree is basically taking average. You take the average of the predict response out of each of these trees. Okay. Okay, so here that's the basic idea of the algorithm for random forest. I show a picture of forest. In a forest, you look at, well, just take a look at the forest. Most likely you see trees are more similar. Okay. But of course, they are also dissimilar, right? There are some dissimilarity as well. So I don't know why this author came up with this interesting idea at first. But I think this committee method is really interesting. Right? You sort of have a lot of models and just go for that. Of course, certainly there's a disadvantage of that because the interpretation is not as easy. So you take average of many models, right? So the prediction is more or less like the break box of predictions. It's hard to tell. Now here, this is general recommendation for the parameters in random forest. For classification, the default value or recommended value for number of input variables involved in each tree is roughly the square root of P. So here, let's say you have 9 variables, so use each tree only involves 3 input variables. So we randomly pick from these 3 input variables. What is the chance of that? 1 out of 9 choose 3, right? Okay. And then for larger problems, like say you have like 500. Let's say you have 500 input variables, so roughly. One guy calculated square root of 500 is about 23, right? Roughly. Anyway, okay. Is it true? Calculator. Okay. Oh, maybe we have our calculator. Remember, we have our big calculator anyway. So. $22 or 23, so roughly, okay, it's come close to that. Anyway, so here that's the ideas of this. Here, the size of the trees involve only this many variables. You get the idea. Because the original idea of this backend is that if you just take all these input variables, say 500 variables, okay, the outcome is very sensitive to just a small change in data variables. Because there's many variables. Okay. And for regression, if you try to use random forest idea to train on regression, the default values for M is roughly a third of the size of the number of variables. So with 500 variables, you probably try to build a tree with like a little bit over 167, so like that. And the minimum node size is 5. These are general recommendations for that. And then for classification, minimum node size is 1. For sure, right? You want a terminal node with 0 observation? That doesn't make sense. Okay, so anyway, so these are general recommendations about, say, the node size and also the number of variables involved in the tree. See, the idea is that if you have a few number of input variables involved in trees, you have a few splits, right? End up with a simpler model. Here, these are basically just general recommendations. Only basically they can be these numbers can be considered as tuning parameters when you try to train your random forest model in the tuning process. In addition to that, remember earlier I mentioned random forest is a random statistical method. This is not exact, right? Okay. So the idea is that the result may not be stable, okay? And also the result may depend on your random start. Okay? So the idea is that try to verify the stabilities of the forest, okay? By say starting with at least 2 different seeds. So rather than just do it once, do it say more than once, twice, 3 times, and so on. So and see the result. And also by increasing the forest size to a sufficiently large number, means that instead of looking at the forest of say only like say 10 trees or 50 trees, probably want to see a larger forest like 500 trees or even 1,000 trees. Of course, that if you grow too many trees in the forest, the runtime for that is going to be quite extensive, right? Okay, but of course there's a trade-off. Okay? In addition, the use of random forest to assess variable importance, okay, should only be interpreted and reported as relative ranking of significant predictors. Okay? Interestingly, this random forest method can also be used to assess a variable importance. Okay, actually, we actually talked about that before. Okay, this is it's sort of useful tool to assess variable importance as well. Okay? And because of this, the randomness features, so the results should only be interpreted and reported as relative ranking, not absolute ranking. An important features of random forest is that its use of so-called out-of-bag samples. Okay. So for each observation, it constructs its random forest predictor, averaging only for those trees corresponding to bootstrap samples where Z is not included. Okay. So excluding this. In a sense, the idea is very similar to Jackknife, right? Isn't it? This is a combination of bootstrap and Jackknife. Jackknife means you exclude certain observations and use the remaining observations to come up with a model and then assess error using those excluded observations. So, anyway, this term comes from the AI community, so that's why. Maybe we say this is Jackknife samples as well. Okay. Now here's some advantage of random forest. It can handle a very large number of predictors. Okay. Usually, a lot of methods were not so good, be very noisy on just a large number of predictors. But here, random forest can handle that. And it estimates the variable importance in determining classification. Okay. This is very different usage of random forest. Instead of building this random classification model, regression model, can use that to determine the variable importance. It also generates internal unbiased estimates of the generalization error. Generalization error is the test error, right? So, and you can also use this method to impute missing value. It's also a good method for imputing missing values as well. Okay? And maintains accuracy even when large proportion of data are missing. So this random forest method is particularly suited for data with large number of missing values. And requires very short training time. This additional use of that, okay, actually at the moment, I didn't put this up. Okay. We can also use this for clustering, means unsupervised learning as well. Okay. Because there's particular features of this random forest is that it allows you to estimate proximities of observation. Proximity means it's a measure of how two observations are similar to each other. Okay. So similar objects can be put together. So that's a task of clustering. We did not talk about that yet. And usually the disadvantage involved in random forest include overfitting, overinterpreting as well, okay, of some data sets, and even more pronounced in noisy classification regression tasks. And they do not handle problems where majority of input variables are irrelevant. That's correlated data. It's really nice for correlated data. I will delay this partial least square for next time. I'm not going to talk about that. Okay. Anyway, so we basically just use software to do that. Okay. There are many software implement that. Okay. I forgot to put random forest before that. Yes, I did it, but when I put this, I forgot to put this. Random forest. Because that means that this random forest does not come with a standard distribution. It's you have to build it, right? You have to install the packages. Okay? Use the install packages and the package name and use depends equal dependencies. I talked about that before, isn't it? Okay. Install package function, the package name, and comma, and dependency equal. When did I talk about that? When I talk about the installations of Caret, right? Okay. Just look at the class notes about that. Okay. You want to build all the dependency trees and also all the suggested package as well. Okay. But anyway, you need to install this package to use this random forest. Okay. Other packages also allows you to do random forest, like Caret has this one. I think probably Caret is built on the dependencies of this. I think. Anyone recall that? I already forgotten about the time that when you build up Caret package instead. In the past, probably at least a day back, more than 10 years ago, and when at that time, S language or S plus, well, this is R is built upon this on top of S language. Actually, use the same the philosophy of that. Okay. I think they didn't use the random C we use nowadays. Usually in all the pages, the random C's that require is supposed to be a prime number. And it's hard to come by with a prime number. Okay. It requires you to put a prime number. Okay. That is no longer needed. You can use that. I just put in a number here. Okay. So it's just with a random C to start with this. Okay. Let's run this our first example. I'll do this twice. So here, this example, random forest call. Here, there's some iris data. Where here, when at the time of building this model, I also request like a variable importance to be evaluated, so we can look at that variable importance as well. Okay. And to save the memories of the object size or the memory size of the output object. Here you can say keep forest equal forest. Because there's disadvantage of using this option. Okay. That means that later on, suppose you want to extract, look at a particular tree in the forest. This will not work. You have to say keep forest equal true. Otherwise, you cannot look at individual trees. Okay. Let's say at the moment we only look at this, and proximity major would be true. It would be nice to look at this proximity major in a graphical way, so we can appreciate this. So proximity also allows you to look at why an individual could be misclassified. Okay? In a sense, there's a way to render this proximity in like Euclidean space, also you can see the distance between 2 points actually reflecting how dissimilar they are. Okay? If 2 points are far away, it means they are more dissimilar. Let's look at that later. So anyway, when you run this, it produces this out-of-bag estimate, so error is 4%, and then here confusion metric, you can see that 6 out of 150, so we have 4% of error rate in this result. It also gives a class error for this one. Basically, we have no misclassified plans for Setosa. This is also true in other classification methods. Within this, we have seen this another time. But there are 6% error rate within each of these two classes. So basically, this is what you expect in output. You can also view this variable importance. It measures in two types of things. Here, first one, this is mean decrease in accuracy base. Here, this is usually classification error. Okay, this is classification error. And this is Gini. Remember we mentioned about this Gini measurements of. When did we talk about this? In the tree model, right? Okay. This is another way to assess the error. Okay, use a Gini function, this impurity function. Okay. So, of course, usually you are more interested in the plot result rather than looking at this. Okay. I didn't put this in the right order. Maybe I should put this up there because we say variable importance. I should put this up. I rearrange that and this is the final result. And you can run this variable important plot. This variable important plot is built in with this random forest package, so you can actually run this. Okay. And I guess in the Caret package, just make use of this variable important plot in random forest. And as we expected, we kind of expect that the petal length and petal width are the two most important variables, right? Isn't it? Okay. They are almost identical, so as an importance. Less so would be this sepal length, and probably well in this margin, so we probably also consider the inclusion of sepal length. Okay. And sepal width has very little bearing on this classification task. As you can see from this, variable importance. So here the number of variables involved in the final model probably between 2 and 3, right? Okay. So this is too simple a model. So we only have 4 variables, okay? And here the following is a plot. This is multi-dimensional scaling, or so-called principal coordinate analysis. So you look at the original scatter of your data set, and then look at the 2 major axes where you produce the most variations on. I hate to talk about this at this moment. This is sort of very similar to principal components analysis. Okay. So the basic idea is by shifting your center to a new center and then do rotation and find two directions that capture the most variations in your data. Okay. Actually, that's the idea of this multi-dimensional scaling. There are different methods of multi-dimensional scaling. One is this so-called classical multi-dimensional scaling, and then this principal component method as well. Okay. So let me run this and try to explain a little bit about this result. Okay. I think we can just do everything here. This is graphics. Okay. This is to combine the 4 measurements with the 2 this so-called principal coordinate directions, or 2 principal coordinates, or in a sense 2 principal components. Okay. Direction, so that you can see. Basically, we can focus more on this. Well, actually, this is the transfer of the other part. Okay. This is second dimension of that is multi-dimensional scaling. Okay, versus first one. So idea is that original we have 4 dimensions and then we only reduce to 2 dimensions. Of course, here the result in the loss of information because we didn't capture all variability. But this too will be enough to capture the majority of the variations in the data set. Okay, we'll talk about that later. Okay. Basically, in this output, okay. This output gives this cumulative proportions of variation captured by the 2 dimensions. The first one already captured about 78% of total variation in your data set. Okay. And cumulative, if you include the 2 dimension, I think the one we see the graphs, you account for about 82% of variation. Okay. Of course, it's still about 18% that we can account for by only looking at 2 dimensions. And the price like this, proximities basically it measure how similar 2 observations are. And if you take a look about whatever this methods lead us, unless we know that. See the mouse pointer point to. Okay. Proximity is actually measure the similarity, how similar two objects, so how close two objects are to each other. Or in this case, this means planes. So it means how similar two planes are. Okay? And 1 minus this proximity means that how dissimilar. Okay? Also give it a sense of distance. Okay? The larger the distance, the less similar two planes are. Right? So actually, whatever this will give you, we try to plot them, and actually this give you, in this 2 dimension, when you look at this plot, okay, the distance actually reflect the actual distance between 2 objects, in some sense, okay. So this you can see that. Well, this is hard to see. I kind of use another command later on to try to blow up this. You can see that. Okay? See, all the setosas are very close to each other, right? They are very similar, right? Okay. There's no any red points that lie close near any one of these two groups. So that's why this setosa can be clearly separated. Okay. Let me blow up this part. So it's really hard to see from this. Okay. And we have, and also this random forest package also have this built-in multi-dimensional scaling plot. Basically, take that, actually can reproduce this graphics. The second dimension on the vertical axis plotted against the first dimension on the horizontal axis. Okay. So let me just bring this up. That means if you really want to produce this multi-dimensional scale plot, you don't have to go through this. You can just take that result directly to that. Okay. So take this random forest fit, okay, and then here this will be the response of interest. And here this is spaced by the colors. Well, this is basically spaced by the colors to use in producing this points of these 3 groups. I use color 2, 3, 4, the red, green, blue. Anyway, so red, green, blue again. And plotting characters, I use the first plotting character, second plotting characters, and third plotting characters for that. Okay. So basically use that for setosa, versicolor, and virginica. So you can see that. This one reproduces that graphics, but only look at the 2 dimensions. Okay. So there's no mistake of classifying setosa from the other 2 groups, right? Okay, because they are, any of these points are quite distant from any points from the other 2 groups, right? Okay, according to this graphics. But it's not the case in classifying. So we say second group is versicolor. Is it really red, green, blue for that? These 3 different iris. What knows? If I know about the color, maybe I use those colors to represent that. Okay. Anyway, so here for example, this versicolor somehow just go into the general scattered of what is that? That's virginica, right? This plus sign. This plants in virginica plants just get too close to this group of versicolor. So most likely this will be misidentified. You can see later on each class has 3 misidentified plants here. These 3 are misidentified, and so these 3 here. Okay, 1, 2, 3 will be misidentified. And actually, there's a way to sort of identify this individual. Okay.
Does identify function work in random forest?
It should say multi-dimensional scale. I'm not sure about this. You may want to try it. There's another way. Later on, I just actually calculated the misidentified the IDs were misidentified. You can use that information to put this in. I didn't try that actually. I didn't try. Maybe this way. I'm just taking it in direct way. Hopefully there will be. I didn't find any identify function in this package, so probably not directly. But we can do it indirectly. I do that in the next types of plot. Okay. Random forest also calculates something called margins. The margins of random forest classifier. Okay. So margins of observations are calculated. So here we have 150 observations. Okay. And the margin of an observation is defined as a proportional vote for the correct class minus a maximum proportional votes for the other classes. So what do we expect? Do we expect a positive value or negative value for individual to be correctly classified? Positive, right? Isn't it? Okay. So proportional votes for the correct class. We hope this number is bigger, is larger than the other one, right? Than the maximum proportional votes for the other classes. So then you would not misidentify. So we can actually see that here this is this is a margin plot of that, and you can see that if I produce, I probably should add the line here. Let's see. Where are we at? Just use the default colors anyway. Oh, I produced it wrong. Okay. So here we create this one, the lines, and actually you can see that there are 1, 2, 3, 4, 5, 6. There are 6 misidentified lengths. Okay. You have this this so-called margin go below 0. Okay. For any observation, that means these observations are misclassified. So this order thing. And this package all allows you to plot outline measurements, outline measures observation. So give you different views of this data set. Okay, in the way that outline measures. Let's just run it and see the result. These are outline measures of the individuals. Okay, red color for Setosa and green. This green color for rosy color. The blue one is for what is that? That's one, Virginica. You can see that within this class, these 3 identities will be the misclassified observations to be seen later. I'm going to enhance this graphic so you can see the individual they are misclassified, and then the misclassified identities for this here, this one, and this one. Okay. Actually, you can enhance this by sort of replace the thick lines of that identities with this misidentified individual. We see that there are 3 misclassified versicolor plants, and then 3 misclassified Virginica. Okay? And by using this command and press the text around it, you can actually see that I go back to the method there. This one was quick. I can do that. I didn't think about this. Probably need to do it. So to add that, let me redo this text command here. So here, these are the misidentified individual. Probably make it larger, much easier to see. Okay. These are the planes are actually misclassified. Okay. So here, this outline majors actually give you the idea of this. Okay. Of course, this is not to be interpreted that well, at certain height this will be misclassified for all classes. Okay, because this is relative. Yeah, this is only within each class. Okay. Within this class, this 3 stands out. Okay, and there's a color for that outline majors within the class that. Okay. According to the random forest algorithm. And the 3 misclassified individuals for the Virginia class are here. That's all about how to present this. Of course, in the example, you only see this. You only see this outline plot. If you use help documentation outline plot, they just do that. Okay. I try to enhance them. Just put in this thicker lines for those misidentified individuals, and also place some text on that. So identify this one. So try to enhance graphics. Let me ask you, what does this mean? Of course, you could find another way of just trying to accomplish this, but I find it's much easier just do that. Okay. Given that the IDs for misclassified identities are 71, 78, and so on, what does this do? Actually, all the observations are greater than 50, right? So this is definitely to be true, right? 2 is 1, 1 plus 1 is 2. So, okay. And then there are only 3 observations greater than 100. 3 of this mis-ID. So there are only 3 observations would be using 3. So it means 3 the third class, which is full. Let's make the trick here. Okay. The same idea can be applied here for the labeling this individuals. Okay. I guess I'm not trying to get into the detail of this, but this is a way to try to enhance this. Okay. So here, basically, this creates some graphical aids about interpreting the outputs. Okay. You can see these outline majors. So this, in each of these two types of planes, 3 observations stands out. Okay. Large outline majors for that. Okay, I find this package somewhat interesting. They have now these different majors that allows you to get it. And remember earlier I mentioned that the random forest should not be run only once. Okay, you probably want to set different seeds. Actually, the one I put down here is not actually using that, but just try to show you. If you are running a random forest with different seeds and different number of trees, for example, you can combine the forest to form yet larger forest. Okay, like this example right here. Okay, you can grow forest or combining forest, or first one is growing forest by adding trees to the already existing forest. Okay. Suppose at the very beginning I had this random forest with 400 trees in it. Okay. So let's run it anyway. Some of this takes time. Okay. It's already done, right? We can see the result of this. Okay. This is out of 400 trees. And this out-of-back estimate 0 is 4.67%. And you can add tree to it by using grow command. So here, let's say we do grow command. Grow this random forest with this additional 100 trees. Yeah, this is really interesting. The command. So you can add to that the already existing trees And then let's say we see the summary result of this. Okay. I think I should add. This they didn't output this. They didn't output confusion metric. This must be something else. I didn't see that. But there's a way to do that. Original for it was with 400 trees there, and here we go with additional 500. I think this must be additional comments and arguments you can control. I didn't look at it. This doesn't help much. You probably use help documentation other than that. Okay. I bet there's some other arguments allow us to control this output, this confusion measure, so you can take a look about the error. Okay, so one way of this is add to already existed random forest additional trees to that. The other way is you can combine the several forests into one. Okay. Like this example. So first I have this IF1, which is about 300 trees, and the second forest 100 trees, and third forest 100 trees combined into the larger trees. Okay. So let me let's do that. And final result is 500 trees. Just add to them by using combine function. Now, in any case, it is very important to do this, okay? Because by default, the volts are changed into fraction, normalized, meaning that, okay? And if you say normalizing volts equal volts, that we just keep the count, the number of volts, but not the normalized volts, okay? So to add the new trees or to combine forests, okay, it's essential to put this argument here, otherwise you won't get the correct result. Okay? And if you want to take a look on this particular trees in the forest, this is way to extract it. Okay? Unfortunately, remember earlier I mentioned that if you say, let's say original fit in here, we are at this, right? This is a model I'm looking at. Original fit in, we say keep forest equal false. Okay? So all the information of these trees are not kept. So to extract trees from such a model is impossible. Okay? So when you want to do that, make sure this keep forest equal true. Otherwise, it's not possible. Actually, so I actually show the example using the update function. So here I take the original random forest and update it with say keep forest equal true. So in a sense, this is new result, right? Okay. And maybe you want to set seed. If you want to get back to original trees, you want to set the same seeds here. Okay. So before running this, you want to set seed for that, and then update this model. And here, this is a look of that particular tree. Okay. Unfortunately, I couldn't find just a plot method or print a good print method about printing this tree. Okay. I suppose that there must be some kind of package that allows you to say, for example, suppose you have 10 trees within this forest, you plot all the trees and see, just give you some idea about examples of this ensemble rendering. Okay. So basically, print something like this, not entirely helpful. And this package also has something called a partial dependence plot. Okay. So let me run this partial dependence plot and look at our graphics. Okay. actually, the idea in this case, I run with the Setosa, so I should indicate that. Okay, so for this particular species, okay, this species particularly associate or dependent on the smaller values of petal width. Okay. I'll go back to original data set to look at the summary. Okay. Guess we did this before, right? Didn't we? We can do this by, how do we do that? I forgot how to do that. Data indices and function, okay? We've seen this before, didn't we? So here, by function summary. Let's look at particular Setosa. Okay. What was this? This is petal width. The petal width for Setosa median 0.246. Okay. Compare with other group, they are much smaller, right? Can you see that? Okay. So Setosa is particularly associated with a smaller petal width. You can see that. Okay. Actually, that is illustrated by this dependency plot, or the partial dependency. It's kind of interesting, right? Isn't it? Okay. And there's a function called tune RF, tune in the random forest that allows you to tune these parameters. Okay. Among others, there's a step factor. Let me just use this simple example. Okay. Simple example of that. Okay. And when you do that, it produces output like this. Okay. Out of back. Here, this is the number of variables involved in each tree, 2. Okay. And out of back error is 4.67%. Okay. And then number of input variable involved is 3, and out of back is 4%, and then 4%. Okay. What does this tell you? Probably three input variables would be the best, right? Is it? Okay. And also at the same time, when you say tune RF, also give you this graphics output. So at least you can see graphically. Okay. There's a significant drop. Well, of course, significance depends on how we define significant. But it is graphically. Okay. You see that. Okay. It's very different with the three involving 3 variables in the trees. The best, it will probably produce the best result. Okay. Actually, also seen we have also seen that on the variable importance plot, right? Where you see that what was the one that was excluded? Sepal was a sepal length or sepal width excluded? And here this part produce the result. Now if you want R to return the final model, the best model, you can add to this. I think it's called do best. Not sure. Okay. I hope this works. Okay. The do best and also this result. This different starting points, of course, to end up with that, right? So remember, this is not exactly this is random statistical method. You might want to train more, so and then we have final result. Okay. So here this is result. Oh, this is very different, right? With different starting seeds, result is a different result. Anyway, just try to train over different, just different method. Okay. Actually, I didn't put a starting seeds here, so you cannot see. And then here you can print the final result. This is final result of the best model. It suggests with 3. So actually, they also not only look at the classification error, they also look at the model simplicity as well. So anyway, here basically suggests the three input variables involved would be the best, right? This model. Let me do this, okay? I'll put this on. I'll put this on mine. So if you want to run without two pairs, it would be this, and then with two pairs, just eliminate this two. Maybe I should put two commands in. Okay. Party package allows you to create random forests of conditional inference trees. Okay. Basically, I briefly mentioned about this this package in that they use some statistical criteria to evaluate the goodness of the tree model. Actually, they claim the result is better than the regular trees. Okay. In order to do that, you need to attach this package, this party package, okay, for this conditional forest. Okay. And let's we do this. Package MASS already have this forensic class. Previous I actually try to ask you to build that. Oh, actually, I actually have shown example how to build this data set, but it's there in their package, in this MASS package already. Okay. So you can attach this data set by issuing this command, okay, to acquiring this data set FGL. Okay. This forensic class example. And try to make sure that the response variable, the target variables, okay, try to make sure it's a factor, otherwise the result is not correct. Okay. So here you can run a SFI or just use class command. And this we see that the target variable is of factor type, otherwise this is not correct. Okay. This is classification task. Okay. When I try to build this this class node, I already tried 1,000 trees. It took about like 7-8 minutes to finish the rest. So I guess to illustrate this in class, I probably need to decrease the size. So let me just use 100. Or you can try with a slightly larger number, maybe 500 or something like that. Okay. The important things about training this is, in addition to use different seeds to run it multiple times, okay, you also need to set up the tuning parameter. Here, number of trees to start with 100, okay, and here the number of input variables is the starting values for number variables is 3. So it's try to go 3 or back and forth between 3 or 2 and 2 or 4. Okay, just run that. So set the control value for this this conditional forest. Let me just run the part of this. See, it takes time. Maybe I should reduce further now. Not even 100. It's take a long time to establish this. But here, anyway, look at this. We use a C forest. So here, this conditional forest, okay, with this model and data as this forensic class, okay, and the control parameters is already specified up there. Okay, so we set that control, okay, up there. I should try this first. Originally, I used 1,000, but I didn't test on the times that we tried to do that. And in addition, my computer this is very old computer. There are algorithms that allows you to run like random forests using several computers running parallel computing. So See, after all this, you try to build separate trees, right? Put together. Okay. Here we already run the variable importance of this result, and you can plot variable importance using like for example, Cleveland dot plot, or you can use other things like dot bar plot as well. Here I only use a Cleveland dot plot. So let's look at the result. Okay. This will just give you the variable importance of all the measurement here. Apparently, magnesium is the most important variable according to this analysis here. Okay. Mg is magnesium, isn't it? It looks like the sodium is the least important one. Okay. And well, on the other hand, if you would like to try to enhance the following comment, based on this so-called panel function, we run this final result. Okay. Sometimes you run this variable importance. Sometimes you get the there are examples where you have negative variable importance as well. Negative doesn't mean that it's not important. If you just go far away from this line, it means that it's still important. Okay, just with different measurement. Okay. And here, basically, when you have variable that extend to the right of that, these are important measures. Okay, like in this case. This was suggested by looking at the absolute value of the minimum of variable importance. Yeah. In our case, all the variable importance turns out to be positive. This is nothing particular, it's just the same dot plot function, but except you particularly build out your panel function to try to plot this. Okay. We use a panel dot plot for that, so basically it's based by the plotting characters and colors and size of the plotting points. Okay. And we have like a 1.2 times the standard size, so slightly larger, so make it larger. And here we also do this panel AB lines, just plot this vertical line so you can reference on that. I guess I'm going to just run examples after this. Okay. I will add more examples and hopefully you can also look at other packages and see how other packages handle this random forest. And before I close this, actually I forgot to mention about this. Probably not so important, but this algorithm is already implemented in a lot of this package. Right? RWCA is another one. Okay. RWCA is another package that they actually install this tree model, tree algorithm based on this algorithm. You can go search at Wikipedia, C4.5. Okay. This is a famous algorithm and proven to be probably not if not the best, at least among the best. Okay, algorithm that actually run efficiently with creating tree. Decision trees is by this Quinlan. Okay. I don't know why they use this name. I'm not sure about that. Anyway, this is algorithm. And I think our part, okay, this recursive partition basically is built on using this algorithm. I think he has a like C library to perform that algorithm anyway. And here this idea, the algorithm, how algorithm works. Okay. Anyway, I'm going to stop our discussion at this point. And I'll continue on this. In fact, our case study sort of falls behind this case, but it's okay. I know that it's not easy, especially for those who are taking 680 and 685 simultaneously. A lot of homework, right? Okay. Let's see.